Okay, the problem that we were doing last time was this example where we were taking the limit as x goes to infinity of a fraction, and the fraction is like 3x squared minus x minus 2 divided by negative 5x squared plus 4x plus 1. Okay, so we are trying to take the limit of a rational function as x goes to infinity. So let's first look at what's happening to the numerator and the denominator separately. So if I look at the numerator, 3x squared minus x minus 2, what is happening to this polynomial as x goes to infinity? Notice that as x goes to infinity, the first term goes to infinity, minus the second term goes to infinity as well, and the third term goes to 2, right? So pretty much it doesn't tell us anything, because remember what I said, if you have infinity, if you have, just because 3x squared and x, they are both going to infinity, doesn't mean their difference is going to go to 0. And the reason is 3x squared is actually becoming large faster than x, right? So that's going to play a role. So how do I come up with the limit of the numerator 3x squared minus x minus 2 as x goes to infinity? Well, the trick is you're going to factor out the dominating term, which is x squared. If you factor that out, you get 3 minus... when you factor out, right, so suppose I have 4 plus 5. If I factor out from this expression 3, what's going to go inside? 4 plus 5. When you factor out 3, it means that you divide each term by 3, right? So you're going to get 4 third plus 5 third, right? Notice that if you multiply out, you get 4 plus 5. You agree with that? So if I factor out x squared, then from the first term I get 3. From the second term I'm going to get 1 over x, right? Because I'll be dividing x by x squared. And in the third term I'll be dividing 2 by x squared. So this is what we would be obtaining. Now notice that this term as x goes to infinity, 1 over x goes to what? If the denominator goes to infinity or negative infinity, and the numerator goes to a non-zero number, what's the limit? What's that? 0. If the denominator has limit infinity or negative infinity, that means the denominator is becoming large, numerator is becoming a non-zero number, then the ratio will become 0, right? Will be getting closer and closer to 0. So this guy has 1 over x goes to 0 as x goes to infinity. So does 2 over x squared, right? 2 over x squared goes to 0 as x goes to infinity. Again, you are dividing 2 by larger and larger denominator, right? Remember I showed you the graph of 1 over x squared? Okay, so then, and this term is going to 3. So altogether, the expression inside the parenthesis has limit 3, right? So altogether, the expression in the parenthesis has limit 3. And this guy has limit what? X squared goes to infinity if x goes to infinity, right? So together, the product will go to infinity, right? Am I making sense? If you have one of the factor is big, then the product will be big, right? One factor is becoming closer and closer to 3, the other factor is getting larger and larger, so the product will get larger and larger. So that's how I can come up with the limit of a polynomial. Now, what you need to realize is the following. We concluded that the limit of this polynomial is what? we concluded that this polynomial has limit what? Infinity as x goes to infinity. Notice that that's the same as the limit of just 3x squared. If I just look at the limit of 3x squared, what is the limit of 3x squared? Infinity. So if you are the value, the behavior of a polynomial function as x goes to infinity or negative infinity is determined by the dominating term. You can remember that? The behavior of a polynomial function when x is big is determined by the dominating term. Okay? So then coming back to my original question, what's the limit of the numerator? Well, all I have to look at is what's the limit of the dominating term, and the limit of the dominating term is infinity. What's the limit of the dominating term in the denominator? As x goes to infinity, negative 5x squared goes to negative infinity, right? Well, does that mean that the limit is negative 1? Well, it's tempting to say that the limit would be negative 1. However, it's not. And remember, infinity, I am writing infinity divided by negative infinity, but do I mean that I'm actually dividing? No, I'm just expressing the idea that the numerator goes to infinity, denominator goes to negative infinity. But I'm not really dividing. These are not numbers. Infinity and negative infinity, these are not numbers. So, why should it not be negative 1? Well, because the numerator might be going to infinity much, much faster than the denominator. Okay, then the limit might be big. On the other hand, if the denominator goes to infinity much faster than the numerator, then the limit might be 0. And if they are going to infinity at about the same rate, then the limit should be a constant number. Am I making sense? Let's look at some silly examples to demonstrate that. So this is again some examples that's going to motivate what we should be doing in this problem. So let's think about x goes to infinity of x divided by x, right? If I look at this limit, what's the limit of the numerator? Well, as x goes to infinity, too boring. As x goes to infinity, the denominator x goes to infinity. So I get infinity over infinity. Well, however, the limit is what? Limit is? What's the limit? Well, x over x is what? X over x is actually 1, right? So the limit is 1. Well, every freshman's dream came true, right? You see infinity over infinity, you divide, and you get 1. Works in this example. However, let's change a little bit. If I take the limit as x goes to infinity of 2x over x, right? Now notice once again I have infinity over infinity, right? However, what's the limit? 2. Well, let's look at another silly example. If I take the limit as x goes to infinity, x squared divided by x, right? And I have infinity over infinity again. However, this time the limit is what? X squared divided by x is just x. So as x goes to infinity, so this is infinity. What's happening here? Well, the numerator is just growing much faster than the denominator, right? That's what's happening. How about this example, where I just switch them, x over x squared. Well, in this case, again, I have infinity over infinity, but now the limit is what? Because what I actually have there is 1 over x, right? X divided by x squared, that's the same as 1 over x, and 1 over x goes to 0 as x goes to infinity, right? Okay, what did I do? Well, I just have to get rid of that. Okay, so this would be 0, And what's happening here? Well, the denominator is now growing much faster than the numerator. Okay. The point of all these examples is that is to make you remember that if you see infinity over infinity, don't conclude that it's 1. Okay. You have to do some algebra and do things that I'm going to tell you what to do to come up with the limit. Okay. So let's go back to this problem that we started with, this one. And in order to come up with the limit, we know that just because it's infinity over negative infinity doesn't mean it's -1. So what do we do to come up with the limit? Well, we do some algebra. And so the algebra here's the limit that we are looking at. Limit as x goes to infinity. What is that again? 3x squared. I'm going to show you first how this is done and then show you a quicker way of determining this. Negative 5x squared plus 4x plus 1. Okay, the trick is you are going to now this trick that I'm applying, it only works for a rational function when x goes to infinity or negative infinity. It doesn't work when x goes to 1 or 2. Okay, so again the trick is the same as I did before. You factor out the dominating term. So if I factor out the dominating term, I get 3 minus 1 over x minus 2 over x squared. And here if I factor out the dominating term, I get negative 5 plus 4 over x plus 1 over x squared. Now let's see that I can cancel out x squared. This guy is going to what? 0. This guy. This guy. This guy. So what am I left with? Negative 3/5. That's the limit, right? Now that you know how this is done, let's look at the quicker way of doing it. The quicker way of doing it is the following. So this is redo. So how are we going to redo this? Well, this limit that I have, anyone knows what am I going to do right now? Some of you have taken calculus before, I know, and you might have seen this. Okay, the limit, remember what I said? The limit of a polynomial, the behavior of a polynomial when x is big is determined by the dominating term. So the limit here would be the same as the limit of the ratio of the dominating terms. So you just take the dominating terms and then you see that you cancel out the x squareds and you're left with negative 3/5, right? Is that making sense? Just look at the dominating terms, simplify, you get the limit. The reason I don't say it before I do it the other way is because this one tells you exactly why the limit, this one gives you a good justification why the limit is negative 3/5. Well, if I tell you this, you wouldn't know why this is true. Why this is true that the limit is determined by the dominating terms. Also, this will not, you cannot apply this trick when x goes to a number, not infinity or negative infinity. So you can apply this trick as long as x goes to infinity or negative infinity, but you cannot apply this when x goes to a finite number. Is that, yeah? What would be the limit? Yeah, okay, so let's do an example like that. Let's say I have the limit as x goes to infinity, 3x squared minus x minus 2. Here I have 5x plus 4x plus 1. Negative or positive doesn't matter. This will be the same as the limit as x goes to infinity of 3. You still take the dominating terms. And now when you cancel out, you are actually not getting negative 3/5. What you're getting is negative 3/5 times x. Now as x goes to infinity, this thing goes to negative infinity. Okay? Is that making sense? Yeah.
Would you simplify it out and use negative to get negative 5x plus 4x?
Negative 5x plus 4x plus 1?
Yeah, so once you make it, negative x plus 1, you add the 4 to the negative.
Oh, going from here to here, what I did is that I am not doing algebra. So this fraction is not equal to this fraction. What I'm saying is that the limit of this fraction is determined only by the dominating term. So the limit of this fraction is the same as the limit of this fraction, but I'm not saying these two fractions are equal.
No, I think it's saying the dominating term is x when we have negative 5x.
Oh, okay. I see what you mean. Yes, I think I took a bad example here. Yes, thank you. I didn't realize that. So this should not be there, okay? If it is there, then I should say negative x instead of negative 5x, yes. Okay. Is everybody okay with that? All right. Next, let's look at a similar but a little bit different example. You take the limit as x goes to infinity, root of 2 x squared plus 1 over 3x minus 5. Okay, what's the limit of the numerator as x goes to infinity? As x goes to infinity, 2x squared plus 1 goes to infinity, so even if you take the root, still goes to infinity, right? And then the denominator goes to infinity as well. And what's the limit? Well, the problem here is that I don't have a polynomial in the numerator. However, it's not too bad. I have a root of a polynomial, right? So still, I know that the limit of the root function will be the same as the root of the limit of the polynomial, right? So what I'm saying that what's the limit of this root function? Well, it's the same as the limit of the side, and then you take the root, right? Well, that means again you can apply the same idea as I said is determined by the dominating term. Okay, so you can just take the limit of the. So if you only keep the dominating terms, what's going to happen? You take the limit as root of 2x squared divided by 3x, right? And x goes to infinity. And then root of 2x squared is the same as what? This is root 2x, right? Divided by 3x. And then x's cancel out. You get root 2 over 3, right? Is that okay? Is that making sense? Well, if you don't look at the dominating terms, you can still just factor out the dominating terms. So another way of doing it would be, which is better but is not as quick as the other one. You factor out the dominating term x squared, and you write it as this. In the denominator, you factor out the dominating term. You get 5 over x, and then as you take the limit, x goes to infinity, root of x squared would be what? X, and then you have root of 2 plus 1 over x squared. Here you have x times 3 minus 5 over x. So if you did all that algebra now, you can cancel out the x's. And now you could say that the limit of this guy is 0, limit of this guy is 0, and you are left with the same thing, root 2 over 3. Is that making sense? Is everybody okay with that? I think a problem like this, I guess probably 8 out of 10 times I probably put it on the first exam. So anything at all? No? Okay, let's move on to the next type of limit problems. Here, sometimes you are given a limit problem where you have a function f of x and minus another function g of x, and what happens is that as x goes to infinity, f of x goes to infinity, and also g of x goes to infinity. So the limit form, when I say limit form, I mean individually, I look at the limit of each term individually and see what I'm getting, okay? So what I'm getting is infinity minus infinity here. Does that mean the limit is 0? Okay, once again, no, because you now understand that one of the term might be going to infinity faster than the other one. So, for example, if I look at the limit of x going to infinity of x minus x, right? Does it have the form infinity minus infinity? Yeah. X goes to infinity, x goes to infinity. But what's the limit? 0, because x minus x is 0. How about this example where x goes to infinity? I have 2x minus x. Again, infinity minus infinity. However, the first term goes to infinity twice as fast as the other one. And what's the limit here? Limit is not 2. 2x minus x is the same as x, right? 2x minus x is x, and as you take the limit of x, you get what? Infinity, right? Is everybody okay? So let's look at a limit where we're going to have this form. However, we have to apply. It's not going to be as simple as x minus x or 2x minus x. So let's look at the limit as x goes to infinity. Oh, by the way, I'm sorry, I forgot to say, this doesn't have to be infinity necessarily. It could be something else as well. Okay. All right. So here's the example: x squared plus 1 minus x. So this is what we have. What's the limit of the first term? The limit of the first term is infinity, because x squared plus 1 has limit infinity, and then the limit of x is also infinity, right? So I have infinity minus infinity. However, the limit is not necessarily 0. So let's see what should be the limit. It could be 0, but I'm saying just because infinity minus infinity doesn't guarantee it's 0. So how should I compute this limit? How should I compute this limit? What algebra do I do? Well, I have no clue. If I have no clue, I try to remember what type of algebra have I done in my life before when I saw an expression like that. Rationalize. In our recent memory, when we reviewed algebra, when we saw roots floating around, one of the tricks that we applied was rationalizing. So we are going to rationalize and see what happens. So this would be the limit as x goes to infinity. Notice that this thing is x squared plus 1, root of that minus x divided by 1. And we are going to rationalize, so we're going to multiply with this plus x divided by the same thing. And when we multiply the two numerators, what do we get? In the denominator, we get x squared plus 1 plus x. That's all we get. In the numerator, I would be getting what? The square. I'm going to get the square of the root of x squared plus 1 minus the square of x, right? So what do I get? If you multiply the two numerators by using FOIL, at the end, you're going to end up with x squared plus 1 minus x squared. You're taking the square of the first term minus the square of the second term here. And if you simplify, you are getting 1 over x squared plus 1 plus x. Now, what's the limit of the numerator? What's the limit of the numerator? Numerator is 1. What's the limit of the denominator? So the limit of the ratio? 0. Okay, remember I said whenever the denominator goes to infinity or negative infinity, the numerator goes to a non-zero number, then the ratio goes to 0. Okay. Well, actually, the numerator goes to any finite number. Sorry, even if the numerator goes to 0, the limit would be still 0, right? Okay. So let me say that again. If the numerator goes to a finite number, the denominator goes to plus or minus infinity, the ratio will go to 0. Can someone tell me what's the limit as x goes to infinity of sine x? What is that limit? Doesn't exist, right? Because as x goes to infinity, the sine function is always varying between negative 1 and 1. So it doesn't approach a single number, right? Am I making sense? So it doesn't exist. Okay, let's think about this for a second. When we are saying, let's say I'm taking the limit as x goes to infinity of a function f of x, and that's a number L. So what are we saying here? It means that as x gets bigger and bigger, the value of the function is getting closer and closer to L. What does it mean graphically? What does it mean graphically? If you look at the graph of f, what does this limit tell us about the graph? Well, let's make some x's here. And let's say the number L is at this height. So let's say this is the line y equals to L. So that means the height of this line is at L. If assuming that L is positive, of course, what does this limit mean in terms of the graph of the function f? Well, f of x, the value of f of x gives you the height of the graph, right? So what this is telling you is that as x gets bigger and bigger, the height of the graph is getting closer and closer to L, right? The height of the graph is getting closer and closer to L. In other words, what it means is that as x gets bigger and bigger, the graph of the function is getting closer and closer to the horizontal line at L. Am I making sense? So this limit means that as x gets bigger and bigger, infinity, the value of the function is the graph of the function is getting closer and closer to that line. There are a couple of ways that can happen. One way that can happen is that maybe the graph is increasing and it is approaching this line like this. So the graph is always increasing, okay? As x gets bigger and bigger, the graph is increasing and getting closer and closer to the line, but it doesn't touch the line. Another thing that can happen is that the graph might be decreasing and getting closer and closer to the line, but it doesn't touch. However, there is another way that can happen. Maybe the graph has something like a sine function in it, and it's a vibrating function. So it might be like this. It's a vibrating function, but what happens is that the gap between the graph and the line is approaching zero. The gap between the graph and the line is approaching zero. So as x gets bigger and bigger, the best way to say this is this limit means as x gets bigger and bigger, the gap between the graph of the function and the line at height L is approaching zero. Okay? What is L here? What is the line at L? What do we call that? Is there a name for it? It's called a horizontal asymptote. It's called a horizontal asymptote. There is a misconception that the graph of a function doesn't cross a horizontal asymptote. That's not true. The graph may cross the horizontal asymptote if you have a function which is vibrating like that. Okay? However, that's true for a vertical asymptote. If you have a vertical asymptote, the graph would not cross the vertical asymptote. Am I making sense? But, even then I can do things like this. Okay, let me say something here about the vertical asymptotes. So, suppose I have a vertical asymptote. So suppose I have y-axis as the vertical asymptote. So think about the graph of 1 over x, right? The graph of 1 over x looks like this when x is positive, right? So I have a vertical asymptote at 0. Notice that if I can define a function like f of x equals to 1 over x for x larger than 0, and I can define it to be 0 when x is equal to 0, right? So then this point will be on the graph as well. Whoops. Am I making sense? But of course the main curve that I have, it doesn't cross the vertical asymptote. Okay? Am I making sense? Now let's just write down the definition of horizontal and vertical asymptotes. So what's the horizontal asymptote? Y equals to L this is a horizontal line, right? This is a horizontal asymptote for a function f if either the limit as x goes to infinity of f of x is L, or the limit as x goes to negative infinity of f of x is L. If one of these limits is L, you have a horizontal asymptote at that height L. So let me give you an example. Did you guys need time to write that down? Let me take a second too. Okay, so let's look at an example. If I take the limit as x goes to infinity of x plus 1 over x, then what do I get? What's this limit? What's the limit? The limit is 1, right? You agree with that? The limit is 1. So y equals to 1 is a horizontal asymptote in this case, right? For this function. You should, if I just give you the function x plus 1 over x, if I ask you find the horizontal asymptotes, you have to find this limit as well as you have to find the limit as x goes to negative infinity of x plus 1 over x. Okay, in this case, even as x goes to negative infinity, what's the limit? 1. Okay, so I don't get a different horizontal asymptote, right? I get the same horizontal asymptote in both cases. Okay, if these two limits are different, then I have two distinct horizontal asymptotes. Am I making sense? Okay. Okay, maybe let me give you the graph of this function. Let's just look at the graph of this function and see what's going on with this function. Now, if I ask you find the horizontal asymptotes of this function, you don't have to draw the graph, of course. You just have to look at the limits and determine what are the horizontal asymptotes. But I'm going to show you the graph just to show you what's going on graphically with this function. Let's say this height here is the height 1. So this is the horizontal asymptote y equals to 1. What's going on with the graph? Well, note that what's going to happen is the following. I haven't defined a vertical asymptote here yet, but this function has a vertical asymptote when x is 0. A vertical asymptote at 0 means near 0 the function blows up, in the sense that the value of the function gets bigger and bigger near that number. So when x is 0, near 0 the function blows up, and that's you have a vertical asymptote. So the graph looks like, so here is 0. The graph of this function looks like the following. It really looks like 1 over x, except that the horizontal asymptote is at y equals to 1, not the x-axis, and it has another part which looks like this. Okay, so that's how the graph of this function looks like. So you can see what's happening as x gets bigger and bigger, the value of the function is getting closer and closer to 1. Same thing happening here. As x gets large and negative, the value is getting closer and closer to 1. Okay, is everybody okay with that? Alright, so what is a vertical asymptote? Let's write that down as well. X equals to a is a vertical asymptote of the function f if the limit as x goes to a from the right or from the left of f of x is infinity or negative infinity. So here I'm really saying four different limits here, right? As x goes to a from the right, if it is infinity or negative infinity. As x goes to a from the left, if it is infinity or negative. As long as one of them is true, you have a vertical asymptote at a. Is that making sense? So, remember what I said about a fraction. Whenever you have a fraction, when do you get infinite limit? I said if the denominator goes to 0 and the numerator goes to a non-zero number, right? Let me rephrase that again, because even if the numerator goes to infinity, that's fine. If the numerator has non-zero limit, the denominator has a limit 0, then the ratio will have limit infinity or negative infinity. So that means if you are looking for vertical asymptotes, you should look for values of x where the denominator is 0. Okay, so here's an example. So let's say I have the following function. Let's say I have the function f of x equals to 1 over x squared minus 1. That's the function that I have. And I'm asking you, what are the vertical asymptotes, right? Well, what you could say, well, let's take x plus 3 here. Okay, so basically you look for the values of x where the denominator vanishes, and the denominator vanishes in this case where? When x is plus or minus 1, right? So notice that if I take the limit, so this is equal to x plus 3 over x minus 1 times x plus 1. And notice that if I take the limit as x goes to 1 of this quantity, it would be plus or minus infinity. I don't care whether it's plus or minus. I don't have to be that specific here. All I care it is plus or minus infinity. And why? As x goes to 1 from the right, let's say. Why? Because the denominator goes to 0. As x goes to 1, the denominator goes to 0, but the numerator has non-zero limit. The numerator has non-zero limit. The denominator has limit 0. The ratio will have limit plus or minus infinity. So that tells you that x equals to 1 is a vertical asymptote. So I have a vertical asymptote x equals to 1. How about x equals to negative 1? Same thing happens with x equals to negative 1. And when you go to negative 1, from the right or left, doesn't matter, the limit is going to be, again, plus or minus infinity. Again, I mean, I could be more precise if I want to, right? I can say it's plus or minus, but I don't have to be. That's why I'm not being precise. So the vertical asymptote is in this case -1. Again, the denominator goes to 0, the numerator goes to a non-zero number, so the limit of the ratio is infinity or negative infinity. Is everybody okay? The biggest mistake that you can make is the following. You are given a function, a rational function like this, and you look for values of x where the denominator vanishes, plus or minus 1, and then you say that, well, I have a vertical asymptote at 1 and -1. But the function that you're given, what happens is that also the numerator vanishes at 1. Well, then you may not have a vertical asymptote at 1 anymore, right? I have 1 minute, but I'm going to use it. Here's an example. If I take the limit as x, let's look at the function x squared minus 1 over x minus 1. And in this case, notice that the denominator vanishes at what? Denominator vanishes at 1. However, 1 is not a vertical asymptote in this case. Notice that the numerator also vanishes at 1, right? The numerator also vanishes at 1. In fact, this is the same as what? This is the same function as x plus 1 when x is not 1. So what's the limit at 1? The limit as x goes to 1, from right or left doesn't matter. The limit of this guy is not infinity, is it? The limit is what? The limit is 2. It's not infinity. So you have to look for values of x where the denominator vanishes, but also be careful whether the numerator also vanishes there. So before you decide the vertical asymptotes, one thing you should do is factor out if possible. And after you factor out everything and cancel out, then decide the vertical asymptotes. I am going to do more examples on this on Wednesday.